Hello and welcome to the BS Academy. So recently IIT Bombay has changed their syllabus a little bit to the each branches. So according to the new syllabus, we have made these charts in our best possible ways, and these charts basically give you an idea how to prepare your own charts, because ultimately you have to make your own charts of every subject, and after that you will get that confidence. So basically these charts will give you the ideas and perfect information after referring all the reference books. Now the next subject is strength of materials, in which we have prepared total 5 charts are there. Let's begin with the first one, in which we'll include the basics as well as the simple stress and strain, and after the plane stress conditions. Before that, if you are new to our academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box.
Now let's start with some introduction about the strength of materials. Basically, in the applied mechanics, it is the branch of science which deals with the study of forces and their efforts over the body. Here in the forces, external plus internal forces, and in the body it includes rigid plus deformable. So here applied mechanics divided into three parts. First one is the engineering mechanics, then the second one is strength of materials, and the third one is fluid mechanics. So strength of materials, it is the branch of applied mechanics which deals with the internal resisting force and the deformation due to the externally applied load. And the basics of the strength of materials is used while designing any machine component or structure. It is one part of the applied mechanics. The examples or all the concepts we will include is only about the externally applied load. Now there are some assumptions which are taken in strength of materials. First one is materials should be isotropic or homogeneous. Then second one is member or body should be prismatic. Then third one is materials should obey the Hooke's law. Then fourth one is externally applied load must be gradually applied load. Then number fifth, member or body should be in static equilibrium, and Saint Venant's principle is applicable. Then sixth one is analysis is done on the basis of ensuring stress and strain only. Here effect of true stress and strain are neglected. Then seventh one is effect of body forces are neglected. Analysis is done on the basis of surface forces only. And number 8 is effect of residual stresses are neglected. Then number 9, the body should be deformable and it should be continuous. Then deformations should be within the limits only. Here note that if the above listed assumptions are valid, then only the strength of material equations will give the exact value of the stress strain and the deformation. Here factor of safety is used while designing because to follow these all assumptions which are really hard in the real life. Let's start with the basics. Once again, these all are very basic concepts and formulas of all subjects of, but it will be really helpful to understand the concepts of the strength of materials during all the subject. First one, the diagram of homogeneous body and the isotropic body. The homogeneous body is independent with respect to the location, and the isotropic body is independent with respect to the direction. And third one is the anisotropic body. It neither homogeneous nor isotropic. Then fourth one is orthotropic body. In the orthotropic body, properties are different in all three perpendicular or all three orthogonal directions. And fifth one is prismatic body. For that, same cross section throughout the whole body. Here three types of load. First one is static, then fatigue, and third one is impact. Then after engineering stress is equal to P by A and true stress is equal to P by AI, where in the engineering stress you have to take the original area, and in the true strain you have to take the area after deformation.
As you can see here, first one is the load. It is any external force or couple to which a member is subjected during its functionality. And there are two types of load. First one is normal load, second one is shear load. Normal load is always perpendicular to the cross-sectional area and shear load is parallel to the cross-sectional area. Then after one diagram for the axial tensile load, then after eccentric axial compression load and eccentric axial tensile load. So S for transverse shear load and T for eccentric transverse shear load. Then after couples, here two types of couples are there. First one is bending moment couple, which is about the transverse direction, and turning moment couple is about the longitudinal axis. Then there are some examples are there. First one is for finding the turning couple at A, then second one is for finding the turning couple at X section, then third one is for finding the bending couples. Then after shifting load is there. If you want to shift the load from one point to another point, then you have to add one couple for that load, and here by applying two axial eccentric load it can produce the pure bending couple. Then after classification of stress, first one is the normal stress and the second one is shear stress. Normal stress, it include two types. First one is direct normal stress and the second one is indirect normal stress or bending stress. And the equation for the stress you can use here, m by INA is equal to sigma by y is equal to E by R. And the second equation for shear stress, tau is equal to V A y bar upon INA into V, and T by J is equal to tau by R is equal to G theta by L. Then after coming towards the strain, here normal strain, then after shear strain. Normal strain is axial or linear strain, you can say that. Here epsilon x is equal to delta L by Lg. Similarly, epsilon y is equal to delta h by h, and epsilon z is equal to delta b by b. Here L for length, h for height, and b for width. And after shear stress, it is the change in angle between any two planes which were originally at right angles, and phi is equal to theta 1 plus theta 2. Then third one is volumetric strain. Epsilon v is equal to change in volume by original volume. Epsilon v is equal to epsilon x plus epsilon y plus epsilon z. There are 9 terms for the stress in the direction of x, y and z. Then E is equal to 2g into 1 plus mu, and E is equal to 3k into 1 minus 2 mu, and E greater than k greater than g. This note is very useful in the examination. In every year there may be questions for the equation of E, G and mu. Then here for the material of homogeneous and isotropic, the minimum number of elastic constraints required are 2. Then for orthotropic 9 constants are required, and for the anisotropic 21 constants are required. Then after Poisson's ratio, mu is equal to lateral strain by longitudinal strain, and mu is equal to minus epsilon y by epsilon x, and epsilon y is equal to epsilon z. Then minus 1 less than or equal to mu less than or equal to 0.5. Then there are some values of mu for general material. Mu is equal to 0 for coke, then mu is equal to 0.1 to 0.2 for concrete, then mu is equal to 0.3 for steel, then 0.25 to 0.33 for engineering materials, then 0.49 which is near equal to 0.5 which is for rubber. This value of mu is important for the rubber. Then mu is 0.5 for all incompressible materials. Then for general, mu is equal to 0.33 and k is equal to E. Then after 2D plane stress system, for that the equation is there. Then examples are beams and shaft. And for 1D loading, sigma is equal to sigma xx 1 cross 1. Examples are like bar, rod and column. Then strain system is there. The equation for epsilon you can see there. And then there is one table for stress strain system and total number of sigma or epsilon component needed and independent number of epsilon component required. Here for 3D, 9 components are needed and from that 6 are independent. For 2D, 4 components are needed and from there 3 are independent. And for 1D, 1 component is needed and that is independent component. And then after elastic constant, first one is Young's modulus. E is equal to sigma by epsilon, which is equal to stress by strain. And here note that sigma is equal to constant for material, and if E will increase then epsilon will decrease. Then shear modulus G is equal to tau by phi. Then shear modulus is also known as the modulus of rigidity. Then third one is bulk modulus. It is only designed for the hydrostatic pressure condition, where sigma x is equal to sigma y is equal to sigma z is equal to p. K is equal to p by epsilon v. So you can say that K is equal to p by del v by v. From there delta v is equal to pv by k. These equations you can use in the MCQs. Then after longitudinal strain, it is normal strain in the direction of load, and lateral strain, which is transverse strain, it is the normal strain in a direction which is perpendicular to the direction of load. Every longitudinal strain is associated with two lateral strain, and nature of longitudinal and lateral are opposite to each other. So this is all about the basics of the strength of materials. So from the basics, the equation of normal stress and shear stress is very useful in the XOM as well as the MDID, and the equations of E, Kg and mu in the terms of each other is also very useful. Now in the second chart we'll include 3 chapters are there. From the first one we'll keep some basics also there. Now in the second chart we'll include the 3 chapters are there. First one in which we'll include some more basics like Hooke's law, then thermal stress, then after axial deformation. Then in the second chapter centroid and moment of inertia, and the third chapter will be SFD and BMD. So if you like this video, please do like and subscribe to the BS Academy and press the bell icon for the upcoming charts of strength of material. Hello and welcome to the BS Academy. We hope that your preparation is going well. Now in the second chart of strength of materials will include there are 3 chapters. First one is the basics, then after the centroid and moment of inertia, and the third one is SFD and BMD. Let's begin one by one. First one is Hooke's law. Before that, if you are new to your academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box. Here you can see that in the Hooke's law there are 3 equations for the direction of Ex, Ey and Ez. For the direction of x, here epsilon x is equal to sigma x by E. Then for y direction, mu into sigma by E, and for z direction epsilon z is equal to mu into sigma by E, where mu is equal to minus epsilon y by epsilon x. Then after the second one is general Hooke's law. For that 3 equations are there for 3 different directions. Ex is equal to sigma x by E minus mu into sigma y by E minus mu into sigma z upon E. Then after for y direction epsilon y is equal to sigma y by E minus mu into sigma x by E minus mu into sigma z by E. Then for the z direction epsilon z is equal to sigma z by E minus k into sigma y by E minus mu into sigma x upon E. Here a plane stress system need not necessarily will results into a plane strain system. Then after a uniform bar lying in the x direction is subjected to the pure bending, which one of the following tensors represents the strain variations when bending moment is applied about z-axis. then the equations will be like epsilon x is equal to sigma x by E, and epsilon y is equal to minus mu into sigma x upon E, and epsilon z is equal to minus mu into sigma x upon E. Then after the applications of general Hooke's law, there are two cases. First one is a rectangular bar subjected to 3D stresses, and the second one is solid cylinder shaft. So for the first case, epsilon v is equal to 1 minus 2 mu upon E into sigma x plus sigma y plus sigma z, and for the second case, epsilon v is equal to epsilon l plus epsilon d plus epsilon d. Here epsilon v is equal to epsilon l plus 2 into epsilon d. Then after thermal stresses, it is a secondary type of stress because primary stress comes due to load only. Then delta x is equal to alpha L delta T. This equation is very useful. Then for a bar which is hinged from one end, then the equation epsilon v is equal to 3 into alpha delta T, and epsilon v is equal to 3 into epsilon D. Here for prismatic bar is fixed from x and y direction, then you have to use directly this equation of sigma is equal to minus E into alpha dt upon 1 minus mu. And if a cube is fixed from all three directions, then sigma is equal to minus 3 into alpha dt upon 1 minus 2 mu. Then for composite bar or compound bar, the equation will be like sigma L upon ES plus alpha L delta T of S, which is equal to alpha L delta T of Cu minus sigma L upon E of Cu. Then there are some examples there. Then after thermal stress calculation, here first one is prismatic bar is fixed between the two rigid supports along the length in the x direction. So the equation will be like sigma T is equal to E into alpha delta T, which is thermal stress, and sigma is equal to minus E into alpha dt. Then after in the second case, if alpha dt into L is greater than the stress produced, then sigma x is equal to minus E into alpha dt plus E into delta by L. Then in the fourth case, when the bar is fixed from the both the side, then sigma t is equal to minus E into alpha dt by 2, which is equal to sigma. Here the value of sigma and sigma t will be same. Then for this type of composite beam, sigma is equal to minus E into alpha dt by 2, and for the cube which is fixed from all the sides, then delta x is equal to alpha L delta t into 1 plus mu. Then for the compound bar, there are four cases are there. Here in the first case, face to face connection, and if temperature will increase, then you can use the equation of sigma L upon E of S plus alpha L delta T of S, which is equal to alpha L delta T of Cu minus sigma L upon E of Cu. So similarly for the three cases, you can write down this equation. The second case is for the face to face and temperature will decrease. Then third case is for fixed between two supports and temperature will increase. And the fourth case, in which fixed between two supports and temperature will. So you can use the equation of sigma L upon E of S minus L alpha dt of S plus sigma L upon E of Cu minus L alpha d of Cu, which is equal to 0. So by using this equation, you can find the value of any of the term like sigma or E or L. Now then after axial deformation is there. For that there are three cases. First one is for prismatic bar. You can see the diagram here, and the equation of deflection delta is equal to PL upon A, which is equal to sigma L upon E. And here note that For spring, if axial load is applied, then K is equal to E upon L, and here K is proportional to A, proportional to E, and proportional to 1 by L. Then for the non-prismatic bar, delta L is equal to PL upon A, and delta L is equal to delta L1 plus delta L2 plus delta L3. Then for solid sphere, epsilon V is equal to 3 into epsilon D. Here circular tapered bar, then equation of delta L will be 4PL upon Y into E into D1 D2, and for square tapered bar, delta L is equal to PL upon AB. Then after for rectangular tapered bar with constant thickness, delta L is equal to PL upon B2 minus B1 into T into E to ln B2 by B1. Then for self-weight deformation, first one is the prismatic bar, delta L is equal to gamma L square upon 2E, which is equal to WL upon 2A, and delta L is proportional to L square. Then W is equal to gamma A into L. Then second one is for conical bar, delta L is equal to gamma L square by 6 into E, and gamma is equal to 1 upon 3 into A into X. Here area of X section is there. Then in the third case, a bar of uniform strength, then sigma is equal to W by A, then sigma XX is equal to gamma X, and delta L is equal to rho into W square into L cube upon 3 into E. Then by compatibility, delta L of solid is equal to delta L of hollow. Then P1 L upon A1 E1 is equal to P2 L upon A2 E2. Then there are some sign convention are there. First one is based on direction. Here in the left direction you can take the positive, and in the right direction you can take the negative. Then in the upward direction you can take positive, and the downward direction negative. Then clockwise is negative and counterclockwise is positive. Here in these short notes, wherever we have used the sign convention, you can consider this sign convention. Then based on the deformation, tensile will be positive and compressive will be negative. Then for sagging, it will be positive and counterclockwise. Then for hogging, it will be negative and clockwise direction. Now the next topic is circumferential, diametral, or you can say that the hoop stress. Here diameter of wooden wheel is equal to capital D, and diameter of steel wheel is equal to D. Here D less than capital D, and as temperature will increase, then D dash will greater than that of D. Then here circumferential strength epsilon H is equal to D minus D by D. Then sigma H is equal to E into D minus D by D. Then minimum increase in the temperature, epsilon H is equal to epsilon T, and delta T is equal to 1 upon alpha into capital D minus D by D. Here sigma T is equal to E into alpha dt. Here note that for the hoop stress conditions, in the steel ring the tensile stress is produced, and in the wooden steel compressive stress is produced, and for cross-sectional sigma Fy is equal to 0. Then you can use the equation of sigma W into AW, which is equal to sigma H into AS. Then the next chapter is centroid and moment of inertia. Then here first one is center of mass. It is the point where total mass of the body can be assumed. Then second one is the center of gravity, and the third one is centroid. All the area can be considered at a point. Then here note that center of mass and center of gravity is identical if the solid body is placed in uniform gravitational field. Then centroid will always less than axis of the symmetry, and here in the strength of materials analysis is done on the basis of cross section, and it's a plane geometry. Hence centroid is used in the strength of materials. Now for the moment, it is the total load acting at the centroid. Then MO is equal to WL square by 2 for the bar. Then there are two methods. First one is the integration method and the second one is the by parts method. It is used when stepped bar is there and bodies like I or T shape or L or H or E shape. Then you can use X bar is equal to sigma AI into Xi bar upon sigma AI. Then Y bar is equal to sigma AI into YI bar upon sigma AI. Then there are two examples. You can take a screenshot and calculate it. Then moment of inertia Iy is equal to integration A x square into dA. Then three examples are there for finding the moment of inertia. Then here two notes are there for the conical shape. X bar is equal to 2r upon 3 into alpha into sine alpha. Second one is for this type of shape the centroid is at the distance of minus r upon 6. These two questions were asked in the examination frequently. Then here parallel axis theorem is there. It is used to transfer the moment of inertia from centroidal axis to the another parallel axis, and Ix is equal to Ixc plus A into k square. Here Ix greater than Ixc. Then for the perpendicular axis theorem, Iz is equal to Ix plus Iy. Here Izc is equal to pi by 32 into d raised to 4 for the sphere, and J is equal to Ix plus Iy. Then here note that at a point the sigma I about any two mutually perpendicular set of the axis remains constant. Then the next chapter is SFD and BMD. Here beam is an structural member which is mainly subjected to the shearing, and due to the variation of load SF and BM is also varied. To find the maximum shear force and bending moment or variation, the SFD and BMD is drawn. Then after the types of support, first one is the fixed support, then after hinge support, and the third one is the roller support. Then types of beam, first one is the SSB, in simply supported beam. Then the second one is cantilever beam. Then third one is overhanging beam, and fourth one is continuous beam. Then fifth one is probe cantilever beam. Then sixth one is fixed beam. Then after types of loads, then the second one is uniform distribution load, and the third one is uniform varying load. Then calculation of reaction forces. For that there are some examples are there. Then there are calculation of reaction forces. In the first example, the point load is acting at the center and you have to find the reaction at C and A. And in the second example, you can see that here you have to find the value of RA and RC. Here uniform distribution load is applied. Then for the third example, UL is applied and you have to find the RA and RB. So these three examples for the three different types of load. Then in the fourth type, the combination of UDL and point load. Then in the fifth example, UL is applied. Then here note for the SFD and BMDs for the three types of load. Here for the first one, in which no loading between 2 points, then the SFD will be like rectangular and BMD will be like triangular. Then for the UDL, the shape will be linear and BMD will be parabola. Then for the third one, UL, W is proportional to X. Then SFD will be parabola and BMD will be cubic parabola. These shapes of each type you have to remember. In the examination sometimes the shapes were asked. So these are about the second chart of the strength of materials. Now in the third chart we will include the most important chapter from the strength of materials, the slope and deflection, and also we'll include the theory of pure bending in the third chart. So if you like this video, please do like and subscribe to the BS Academy, and please share this video to your friends also who is preparing for the GATE examination. Thank you so much.
Yeah, come on, bring it on. There we go.
Hello and welcome to the BS Academy. So recently IIT Bombay has changed their syllabus a little bit to the each branches. So according to the new syllabus, we have made these charts in our best possible ways, and these charts basically give you an idea how to prepare your own charts, because ultimately you have to make your own charts of every subject, and after that you will get that confidence. So basically these charts will give you the ideas and perfect information after referring all the reference books. Now in the third chart of the strength of materials will include the slope and deflection and the theory of pure bendings. Let's begin one by one. First one is slope and deflection. Before that, if you are new to our academy, then please subscribe for the upcoming videos, and the links for the short notes which are in description box. Here you can see that the definition of deflection, it is the vertical displacement of any point from its initial position up to elastic curve, and delta max is less than delta allowable. It is the condition for design of a beam on the basis of stiffness criteria, and the shape of the elastic curve depends on the types of loading. Here note that if SF is equal to 0, then BM is equal to 0, and the diagram will be like straight line and linear curve. Then if SF is equal to 0, then BM will be constant, and the shape of the BM will be like arc of a circle. Then SF is not equal to 0 and BM is also not equal to 0, then the curve will be like parabola, and it will be of second, third or fourth or any order of degree. Then for the straight beam concept, here you can use the equation of delta C is equal to delta B plus BC into theta B. Then after standard formulas from which the questions were so many times asked in the GATE examination, here note that these formulas are valid for only the prismatic beams, and EI is equal to flexural rigidity or bending rigidity. Here for the first type, theta B is equal to ml upon EI, and delta B is equal to ml square upon 2 into EI. Then in the second type, the load is acting at the end, theta B is equal to PL square upon 2 into EI, and delta B is equal to PL cube upon 3 into EI. Then third one, UDL is there, then theta B is equal to WL cube upon 6 into EI, delta B is equal to WL raised to 4 upon 8 into EI. Then for UVL, delta B is equal to WL cube upon 24 into EI, and delta B is equal to WL raised to 4 upon 30 into EI. Then for the fifth type, the load is acting at the center, theta A is equal to theta B is equal to PL square upon 16 into EI, and delta C is equal to PL cube upon 48 EI. Then for the sixth type, theta A is equal to theta B is equal to WL cube upon 24 into EI, and delta C is equal to 5 by 384 into WL raised to 4 upon EI. Then in the seventh type, here the moment will be acting from both the ends, theta A is equal to theta B is equal to ml upon 2 into EI. Then delta C is equal to ml square upon 8 into EI. And for the eighth type,
UL at the center, delta C is equal to WL raised to 4 upon 120 EI. And 10th one, delta C is equal to L square upon 8R, which is the equation for pure bending. Then there is the example: if two bars are connected face to face and rigidity will be 2EI and EI, then theta C is equal to 5 into PL square upon 60 EI, and delta C is equal to 3PL cube upon 60 into EI. Then after superposition principle, for the first one, if the UDL and point load both are acting, then it will be near equal to the equations of UDL and point load. So you can say that delta B is equal to WL raised to 4 upon 8 EI plus PL cube upon 3 into EI. Similarly for the second one, here you can use the equation of delta B is equal to WL raised to 4 upon 8 into EI minus WL raised to 4 upon 30 into EI. Then for the third type, you can use the equation of delta A is equal to 5 upon 384 into WL raised to 4 upon EI. And Maxwell's reciprocal theorem. The equations for the theorem is delta 1 upon P2 is equal to delta 2 by P1, and theta 1 upon M2 is equal to theta 2 by M1. You note that only for concentrated point load and concentrated moments. Then there are some more examples for the values of delta B and delta C. There are methods of finding the deflection. First one is the double integration method or Macula's method. The equation for this method is m is equal to E into I into d square y upon dx square. So you can say that m is equal to E into I into y double dash. Here the final equation will be E into I into y is equal to mx square by 2 plus c1x plus c2. Then the second one is modified Macula method, in which the equation will be like E into I into y is equal to Ra into x cube by 6 plus c1x plus c2 minus p1 into x minus a cube by 6 minus p2 into x cube by 6. Then the third method, area moment method, or you can say that the Morse method. It is used for both the prismatic and non-prismatic bar. In the first theorem, theta B minus theta A is equal to area of diagram M upon EI, and in the second theorem, theta B is equal to area of M upon EI into x bar. So you can find the values of theta B minus theta A by finding the area of M by EI, and for delta B you can find the area of M by EI into x bar. Then fourth one is strain energy method. For this method, the equation of delta, which is equal to integration m into x into del mx upon del p into dx divided by EI. Then theta is equal to integration mx into del mx by delta m into dx divided by EI. And here equation of u will be integration a to b mx square dx upon 2 into EI, which is the equation of strain energy. This method is also known as the Castigliano's method. Then fifth one is the conjugate method. This method is also used for both the type prismatic and non-prismatic bars. Here loading diagram is equal to m by EI diagram of the real beam. First we have to convert the real beam to the conjugate beam. For that, these are some rules for the conversion. You can take a screenshot. Then here SFD of the conjugate beam will be the slope diagram of the real beam, and BMD of the conjugate beam will be the deflection diagram of the real beam, which gives the value of delta B. So these methods you have to use only when the standard formulas you cannot use. Most of the time in the GATE examination, the questions were asked based on the standard formulas only. And sometimes you have to use the superposition principle and the Maxwell principle and the Maxwell's reciprocal theorem. Then after analysis of statically indeterminate beams, Then first one is probe cantilever beam. For this type of beam, unknowns are 4 and equations are 3. So you can use the computability. Delta A is equal to 0 and theta is equal to 0 and delta B is equal to 0. Then for the fixed beam, 6 unknowns are there. And for the third type here, you can use the theta B minus theta A is equal to AS plus AF, and summation of AS plus AF will be 0.
Then there are two special cases. For first one is the beam of uniform strength and the second one is the slicing of beam. Here for the special case of beam of uniform strength, you can use the equation of Z is equal to BD square by 6 and sigma max is equal to 3 into Px by BD square. Then in that also there are two cases are there. First one is depth changing with the constant diameter, and for this type of case sigma max is equal to 3 into Px by B into dx square. Then for second type of case, B is not constant and D is constant. Then sigma max is equal to 3 into Px by Bx into d square. The example is beam of uniform strength and a prismatic bar with the pure bending moment. Then for the second type of cases, then for the second special case, the slicing of beam. Here in that first case is horizontal slicing. Then the equation of Z will be Z solid is equal to B into nt square by 6 and Z slice will be n into bt square by 6. Here n is equal to Z solid by Z slice. Second case is vertical slicing of beam. For this type of beam, for this case Z solid is equal to nt into d square by 6 and Z solid by Z slice is equal to 1. Hence from long beams vertical slicing is more used in the practical cases. Then the next chapter is shear stress in beam. Here tau max always on neutral axis is not necessary. Then after material should be isotropic homogeneous and should follow the Hooke's law. Then third one is shear stress constant E2F and do not change with the width of the cross section B. Then changes along the depth. Here the value of shear stress at any level E2F is given by tau is equal to VA into y bar upon INA into B. Note that because of shear force V, the variation of shear stress is always parabolic along the depth with 0 at the top and bottom and maximum somewhere in the middle, here not necessary at the neutral axis. Then due to shear force V, shear stress will produce on two mutually perpendicular planes. First one is vertical plane parallel to the shear force. The second one is horizontal or longitudinal plane which is perpendicular to the shear force. Then third note is tau average is equal to V by B into D. Then these are some preferable areas which you have to take for the value of y bar. Like in the T shapes, you have to take the y bar from the bottom side, y bar is equal to d by 2. Then for triangle, y bar is equal to 2 by 3 into a from upward side, and for the circular, y bar is equal to 4r by 3 pi, which is for circle and semisphere. These are some values of y bar, which is the centroidal distance from the considered area from NA. Here one more note is there for the values of Z for the different shapes. First one is for rectangular cross section area, Z will be BD square by 6 if the cross section will be vertical, and for the horizontal Z will be BD square by, and for the horizontal Z will be DB square by 6. Then for the square, z of square is greater than that of z of diamond. Then z of r is equal to a cube by 6, and here for z of diamond is equal to a cube by 6 into root 2. And then after the fourth one is for triangle z is equal to bd square by 24. For hollow rectangle z is equal to bd cube minus bd cube by 60. And for solid circular z is equal to pi d cube by 32. Then for hollow circle z is equal to pi d cube by 32 into 1 minus k raised to 4. Here k is equal to di upon d naught, which is less than 1. Then the theory of pure bending, in that some assumptions are there. First one is material should be isotropic, then homogeneous, and should follow the Hooke's law. Then there are 4 types of examples. First one is the strength comparison, and the second one is for the bending stress calculation. So for the first type of questions, you can use the relation of m proportional to z proportional to I by y, and for the second type of question, you can use the equation of m by I is equal to E by R is equal to sigma by y, then sigma max is equal to m by z. Then the third type, here it is the most useful equation, f is equal to sigma max upon y max into a into y bar. Then the fourth type of question, which is for the composite beam, m is equal to E strong by E weaker, then E steel by E wood is greater than 1. Then there are 2 special cases which we have discussed earlier. Then for the top and bottom fletching, the modular ratio will be sigma s upon Es and sigma w by Ew. Here S for the steel and W for the wood. Similarly, for the side fletch, sigma S is equal to m into sigma W. So this is all about the third chart of the strength of materials. Now in the fourth chart of the strength of materials will include the equations of shear stress in beam as well as the theory of pure torsion, and the next one is the complex stress and strain. Hello and welcome to the BS Academy. We hope that your preparation is going well. So let's start the next video. Before that, if you are new to our academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box. Now in the fourth chart of the strength of materials will include there are 4 chapters. First one is the shear stress in beam, and then second one is theory of pure torsion, then third one is complex stress and strain, and the fourth one is strain analysis. Let's begin one by one. Here the first one is shear stress in beam. Here as you can see that shear stress distribution in various cross section. So we have
made the equations for the 5 types of cross section. You can note down that for the rectangular cross section, the tau is equal to VA y bar upon INA into B, and the ratio of T max by T average is equal to 3 by 2. Then for the circular cross section, tau average is equal to V by pi r square, and the ratio of tau max by tau average will be 4 by 3. Then for the triangle shape cross section, tau max upon tau average is equal to 3 by 2, and tau na upon tau average will be 4 by 3. Then for diamond shape, tau na less than tau max, and tau max by tau average will be 9 by 8, and tau na upon tau average is equal to 1. Then after for the I section, tau f is equal to VA y bar upon INA into B, and tau w is equal to VI bar upon INA into B. Here, tau is proportional to 1 upon V, and Tf less than Tw. In general, you can note down this table also because it is very useful. For the rectangular cross section, the ratio of tau max and tau average as well as the tau na upon tau average. You can see here the value of first one is 3 by 2 and 1. Then for circle 4 by 3 and 1. For triangle 3 by 2 and 4 by 3. And for diamond 9 by 8 and 1. For I section it is 3 by 2 and 1. Based on this ratio, you can solve the question in the examination, because sometimes they will give the value of tau max or tau average, and you have to find the value of tau na or tau average. So these ratios will be helpful for you. So these ratios are very important for the examination. For pure torsion, SL, BM and AL is equal to 0, and TM is not equal to 0. Here SL for shear load, BM for bending moment and AL for axial load. All these are 0, but turning moment is not equal to 0. Sign convection, you can take positive for the clockwise and negative for the counterclockwise. Then there are some assumptions for the theory of pure torsion. First one is the material should be isotropic and homogeneous. Then second one is variation of the shear strain across any diameter will be linear with 0 at center and maximum at all the points of outer periphery. Then phi max is equal to all the points on the periphery, and phi is proportional to r. Then third one is theory of pure torsion is only valid for the pure torsion. Then for bending and twisting there are some equations. These will be very helpful in the examination. First one is m by INA is equal to sigma by y, which is equal to sigma max upon y max, which is equal to V by r. Then similarly for the twisting, T by J is equal to tau by r, which is equal to tau max upon r is equal to g theta upon L. Then Zp is equal to J by r, which is polar section modulus. Then Z is equal to INA by y max. Then third one is sigma max is equal to m by z for bending. Similarly for the twisting, tau max is equal to tau by Zp. Then EI is equal to flexural rigidity. In the twisting, Gj is equal to torsional rigidity. Then AE upon L is equal to axial stiffness, and T by theta is equal to Gj upon L is equal to Kt, which is known as the torsional stiffness. So from this table you can remember by comparing the equations. Then after torsion equation is there, T by J is equal to G theta upon L is equal to tau by R, which is equal to tau max upon R. Here T for the applied or resisting turning moment, and R for radius of gyration, J for polar moment of inertia, tau for shear stress at radial distance r from center, and G is equal to modulus of rigidity, theta is equal to angle of twist, and phi for shear strain or shear angle. Then L phi is equal to r into theta. This is also important for the pure torsion. Then after for solid circular cross section, Zp is equal to pi by 16 into d cube, and J is equal to pi by 32 d raised to 4. Then for hollow circular cross section, tau max by d0 by 2 is equal to tau min by di by 2. Then Zp is equal to J by r is equal to pi d cube by 16 into 1 minus k raised to 4. then k is equal to d naught by do less than 1, then j is equal to pi by 32 do raised to 4 minus di raised to 4, where r is equal to do by 2. Then these four equations are very useful in the examination of relation between E, G, K and mu. From these equations every year there may be one questions for the finding the value of E, G, K or mu. So here first one is E is equal to 2G into 1 plus mu, then E is equal to 3K into 1 minus 2 mu. Third one is E is equal to 2G into 1 plus 1 upon m, because mu is equal to 1 upon m. Then E is equal to 3K into 1 minus 2 by m. Similarly, E is equal to 9 kg upon g plus 3k. Here tau is equal to mu du by dy. So these equations are useful in the examination. Then after power transmission by shaft, here the equation of P will be 2 pi nt by 60, where omega is equal to 2 pi n upon 60. Then here note that Z of solid is greater than Z of hollow and Zp of solid is less than Zp of hollow. Here Z for the section modulus and Zp for the polar section modulus. Then after connection of shafts, first one is the series connection. The equation will be theta c by a is equal to theta cb plus theta ba, which is equal to theta ca is equal to T1 L1 upon G1 J1 plus minus T2 plus T1 into L2 divided by G2 into J2. Then for the parallel connection, the equation will be like minus Tc into L1 upon G1 J1 plus minus Tc plus T into L2 upon G2 J2 is equal to 0. Then these two equations also you can use for finding the values of T or J. Here by static equilibrium, Ts plus Th is equal to T, and by compatibility, Ts into L upon G into J of solid is equal to T into L upon G into J of hollow. So in general, till now, for the four types of equations we have used, first one is for axial load, you have to remember sigma is equal to P by A. Then for bending, you have to remember m by I n is equal to sigma by y is equal to E by r, and sigma max is equal to m by z. Then for the third one, shear load, tau is equal to Va y bar upon INA into B, and for the torsion, tau max is equal to T by Zp. Then after the next chapter is complex stress and strain. Here stress and strain on the inclined plane is known as the complex stress and strain, and because of an axial load, normal and shear both will come on the inclined plane. Then principal stress, the definition for that, it is the normal stress acting on the principal plane as brittle material are weakest in torsion. Therefore, the maximum principal stress is required, and sigma 1 max is principal stress theory. Then ductile materials are weakest in the shear. For that we have to find the tau max, and you can use the maximum shear stress theory. Similarly, for finding the sigma 1 max, you can use the principal shear stress theory. Then here resulting stress sigma r is equal to under root sigma theta square plus tau xy square. Then tan alpha is equal to tau into theta by sigma theta. Then the equation of sigma theta will be sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sin 2 theta. And for tau theta, the equation will be tau theta is equal to minus sigma x minus sigma y by 2 into sin 2 theta plus tau xy into cos 2 theta. Then design of brittle material, here tan 2 theta P is equal to 2 into tau xy by sigma x minus sigma y, and sigma 1 2 is equal to sigma x plus sigma y by 2 plus or minus under root sigma x minus sigma y by 2 square plus tau xy square. Then for tau max is equal to under root of sigma x minus sigma y by 2 square plus tau xy square. These equations we have discussed in the MDID also. Then after sigma 1 plus sigma 2, which is equal to sigma x plus sigma y,
and sigma xx is equal to sigma yy is equal to sigma average, which is equal to sigma 1 plus sigma 2 by 2. Then tau xy is equal to sigma 1 minus sigma by 2, and take the mode of that equation, which is equal to tau max. Then tau xy is equal to mode of sigma 1 minus sigma 2 by 2, which is equal to tau max. The equation for tau theta minus in bracket sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. Then here for tau maximum, theta s1 is theta p1 plus 45 degree and theta s2 is theta p2 plus 45 degree. Then epsilon 1 is equal to sigma 1 upon e minus mu into sigma 2 upon e. Here phi is equal to g theta upon L. Here phi is equal to g theta upon L and e is equal to 2g into 1 plus mu. Then after for the combined bending and twisting, the equation will be sigma 1 2, which is equal to 16 by pi d cube into m plus or minus under root m square plus t square. Then sigma max is equal to sigma 1 minus sigma 2 by 2, which is equal to 16. Then sigma max is equal to mode of sigma 1 minus sigma 2 by 2, which is equal to 16 by pi d cube under root m square plus t square. Then after sigma 1 is equal to 32 me upon pi d cube and m is equal to 1 by 2 in bracket m plus under root m square plus t square. Then equivalent twisting moment t is equal to under root m square plus t square. These all equations we can use in the machine design also, and the complete short note for the machine design you can check the link in the description box. And here in the Mohr circle, r is equal to under root sigma x minus sigma y by 2 square plus tau xy square. Then tau max is equal to sigma 1 minus sigma 2 by 2 and sigma average is equal to sigma 1 plus sigma 2 by 2. Then resultant will be under root sigma average square plus tau max square and theta dash is equal to 2 theta, where here theta dash is equal to angle in Mohr circle. Then d is equal to sigma 1 minus sigma 2, d for the diameter here. Then some special cases are there for Mohr circles. You can take a screenshot for that special cases. Now the next chapter is strain analysis. Here for the first one, in the strain analysis for inclined plane, epsilon theta is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 into cos 2 theta plus 5xy by 2 into sin 2 theta. Then for principal plane, tan 2 theta into p is equal to 5xy by epsilon x minus epsilon y, and for principal strain, epsilon 1 or 2 is equal to epsilon x plus epsilon y by 2 plus or minus under root epsilon x minus epsilon y by 2 square plus 5xy by 2 square. Here the equation will be same as the sigma 1 2, but you have to replace the tau xy by 5xy by 2. Then epsilon 1 is equal to sigma 1 upon e minus mu into sigma 2 by e. Then epsilon 2 is equal to sigma 2 by e minus mu into sigma 1 upon e. Maximum of, then after equation of maximum shear strain, phi max or phi absolute is equal to maximum of mod of epsilon 1 minus epsilon 2 or mod of epsilon 2 minus epsilon 3 or mod of epsilon 3 minus epsilon 1. Then after Lamè's equation is there, sigma 1 is equal to e by 1 minus mu square and epsilon 1 plus mu into epsilon 2. Similarly for the sigma 2 the equation is there. Then after strain rosette is there, it is the arrangement of 3 strain gauges in 3 different directions. And here note that the measurement of shear strain is not practical because no such instrument is available, but with the help of this combination we can measure the shear strain. So basically the strain rosettes are used for measuring the shear strain. Here 3 different types of strain rosette are there. First one is the rectangular, then after the delta, and third one is the star. Here the angles for the 3 types, you can note down that angles. Now for the impact loading, the equation of IF is very useful. IF is equal to 1 plus under root 1 plus 2h by delta st.
Then after strain gauges, here it is a device which is used to measure the normal strain when it is less than 0.001 for measuring normal strain. And first one is optimal strain gauge, then after mechanical strain gauge, and third one is electrical strain gauge. First two are works on the magnification achieved. Then after strain energy due to the basic loading, there are four equations. First one is for axial load, U is equal to integration px square dx upon 2 into A. Then after for the CL load, U is equal to integration of Vx square dx upon 2 into Ag. Then for bending, U is equal to integration of Mx square dx upon 2 into Ei. And for twisting, U is equal to integration of Tx square dx upon 2 into Gj. So you can say that U is equal to T square L upon 2 into Gj. Then U is equal to 1 by 2 into T into theta. Now the next topic is strain energy. For that, strain energy is the form of energy which is stored in the material due to externally applied load. And here the equation of U will be 1 by 2 into P into delta, and delta is equal to PL upon AE. Then U by volume is equal to 1 by 2 into sigma into E, which is known as the toughness. And this equation is very useful in the examination. U by volume is equal to sigma square upon 2E, which is equal to 1 by 2 into E into epsilon square. Then after strain energy stored in the bar due to self weight, U is equal to gamma square A into L cube upon 6 into E. So you can also say that U is equal to P square L upon 2 into A into E. So this is all about the fourth chart of the strength of materials, in which we have discussed about the shear stress in beam, then after the theory of pure torsion, then third one is the complex stress and strain, and at the last the strain analysis. Now in the fifth and the final chart of the strength of materials will include the theory of columns and the pressure vessels.
Hello and welcome to the BS Academy. We hope that your preparation is going well. So let's start the next video. Before that, if you are new to your academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box. In the fifth chart of the strength of materials, this is the final chart of strength of materials. In this chart, we'll discuss the remaining chapters are theories of columns, and the next one is the pressure vessel. Let's begin with the first one, which is theory of columns. As you can see here in the theory of columns, the first one is the difference between columns and struts. In the columns, there are vertical compression member, and the struts are compression member in any position. Then all columns are struts, but you cannot say that all struts are columns. Then after short columns is gone under the crushing, and long column is gone under the buckling. These are very basics, but some important topics are there. Then after buckling, it is the special case of bending, which happens only in the long columns due to axial compressive load. An example is bamboo. Then buckling load is PB, and sigma B is equal to PB upon A, which is buckling stress. Then for crushing, sigma C is equal to PC upon A. Here for safe design, sigma should less than sigma C and sigma should less than sigma B. And after design of short column, for that you can use the equation of FC is equal to sigma C into cross sectional area. Then F is equal to FC upon FOS. Then after four columns, Euler's theory is there for the long columns. Here if K will increase, then buckling will decrease, and the equation of P will be pi square EI mean upon L square, and PB upon A is equal to sigma B is equal to pi square E upon lambda square.
Here this equation of P is very useful in the examination because the question based on this equation were asked more than 2 to 3 times. So remember that P or PB, which is equal to pi square EI mean upon L square. Then radius of gyration I is equal to AK square. Here K is equal to under root I upon A and K is equal to D by 4. Then after Rankine theory, for that PR is equal to sigma C into A upon 1 plus alpha lambda square. Here alpha is equal to sigma C upon pi square into E. Then after Rankine's theory for the long and short columns, first one is for long columns, it fails due to the buckling where sigma B less than sigma C and K is higher than buckling is lower. Then for slenderness ratio, lambda greater than 89 for long column and lambda will be less than 89 for short columns. Then you can remember the equation of lambda is equal to LE upon K min. Then for short columns it fails due to the crushing load. Here sigma B is greater than sigma C and the short column is having the more load carrying capacity. Then after effective length, it is the center to center distance between two successive points of zero bending moment. Here this note is very useful for the hinge type beam. Here L is equal to L for hinge and fixed beam. L is equal to L by root 2. Then after for fixed and fixed type, L is equal to L by 2. And for fixed and free type, L is equal to 2L. Then slenderness ratio, lambda is equal to LE by K min. Here Ixx is equal to AK square of maximum and Iyy is equal to AK square of minimum. Then after the eccentric loaded short columns, first one is for the rectangle, Ex is less than or equal to B by 6 and Ey is less than or equal to D by 6. Then for rhombus, Ex is less than or equal to B by 3 and Ey is less than or equal to D by 3. Then for circle, Ex is less than or equal to R by 4. Here E is the eccentricity value. Here note that generally the columns are made by concrete and it is a brittle material, so tensile stress should be avoided. Then for no tensile stress, then here for the cross section area of rectangle, you can consider the shape of core is rhombus. Then for I section, here also the rhombus. Then for square, you can take the shape of core is square, and for circle the shape of core will be circle. Then after the next chapter is pressure vessel, which is the final chapter of the strength of materials. Here in the thin pressure vessel, the ratio of T by T is greater than or equal to 20, and the examples are like cylinder, cell, etc., and it is used for lower pressure. Then after in the thick pressure vessel, D by T ratio will be less than 20, and the examples are like high pressure boilers, then tanks and gun barrels, etc., and it is used for high pressure. After for thin cylinder, first one is circumferential or diametral or hoop stress. The equation of sigma h is equal to PD by 2T. Then for axial or longitudinal stress, sigma L is equal to PD by 40. Then after note that as there is no shear stress, first one is sigma 1 is equal to sigma h is equal to PD by 2T. Then for sigma 2 is equal to sigma L is equal to PD by 40, and sigma 3 is equal to sigma R is equal to P. Here compressive for thin cylinder. These are the loads from the three directions of sigma R, sigma H and sigma L. Then after maximum shear stress, tau maximum of 1 2 is equal to mod of sigma 1 minus sigma 2 by 2, which is equal to PD by 80. Then tau max 2 3 is equal to mod of sigma 2 minus sigma 3 by 2 is equal to PD by 80. And for tau max of 3 1, mod of sigma 3 minus sigma 1 by 2 is equal to PD by 40, which is tau maximum or tau absolute. Then after strain in the thin cylinder,
Here you can note down the equations of first one is Hooke's strain. Epsilon h is equal to PD by 4TE into 2 minus mu, which is equal to delta D by D. Then sigma L is equal to P end into D upon 4T. Then after sigma h is equal to P local into D upon 2T. Then longitudinal strain epsilon L is equal to PD upon 4T into 1 minus 2 mu is equal to delta L by L. And the third one is volumetric strain epsilon V is equal to PD upon 4T into 5 minus 4 mu, which is equal to delta V by V. These three equations of the strains are useful in the examination. And after the last topic is for the spherical cell, the equation of sigma will be sigma 1 is equal to sigma 2 is equal to sigma h is equal to PD by 4T, which is tensile in nature. Then here no sigma L, so tau max is equal to absolute is equal to PD by 8T. And here neglect the value of sigma 3, which is compressive. Then the last equation for the strain epsilon h is equal to sigma h upon E minus mu into sigma h upon E is equal to delta D by D. So these are the equations you have to remember for the thin cylinder. This is all about the last chart of the strength of materials. So now we have completed the whole subject of the strength of materials, and the links for the other subjects like the production technology, thermodynamics, as well as fluid mechanics, machine design and industrial engineering are in the description box. You can check out the complete short notes for these subjects also. If you like this video, please do like and subscribe to the BS Academy, and we'll start the next subject of the heat transfer, in which we have prepared total 3 charts. Please share this video to your other friends also who is preparing for the GATE examination 2021. Thank you so much.